Thank you very much, Leila. That's too much. Okay. We are going to talk about graph and transformers. First, I'm going to say what this presentation is not. So this is not a presentation about leaderboards. I know that in the data science community, we love leaderboards. This is not what this is about. We are going to talk and explain a few basic concepts that we believe will be building blocks of the future. Okay, so we are Digitas. Leila already introduced us, so we'll go quick on this. First, I will talk to you about our AI lab. So if you recognize a few people from the AI lab, you can definitely go and talk to them. The AI lab is a recent initiative at Digitas where we partner, we create multidisciplinary teams to look at some interesting questions. And for example, for this year, we have been looking at NLP and causality inference. Every week, we meet together, we look at some advances of technology, advances of deep learning, machine learning, you name it. We discuss it, we look at some code sometimes, we look at some papers sometimes, and we present internally. So this is the AI lab, and I thank everyone that is on there because they have participated to the last NLP AI lab that helped us create a product called EmotionXT, or improve a product called EmotionXT. Okay, a brief recap of the world before GNN and transformers. I know that some of you might think there was nothing before GNN and transformers. That's not exactly true. And so we'll go through a little bit of this to see what existed beforehand. First, what was happening in the supervised learning field with natural language processing. So we already had pretty much all the disciplines that you can see now. We had question answering, we had sentiment analysis, we had emotion recognition, though that's a little bit more advanced now that we have transformers. We had named entity recognition, textual entailment, and machine translation. The difference is indeed since 2000, let's say between 2015 and 2017, a lot of those results and those scores have improved dramatically thanks to transformers. Okay, start to the basics. What was happening before? In this box here, you see a sentence. AlphaGo has demonstrated the power of reinforcement learning. And what was happening before is that every word in a sentence was assigned to a particular vector. And we used to call this, well, it is still called one-hot vector. The problem with this is, as you see below, the vocabulary size of your model had to be as big as the number of words you were going to use. Obviously, those vectors were sparse, and we wanted to make them dense sometime to be able to do some better analysis. But the real problem was the dimensionality of the vocabulary you were using. So if you look, for example, at this sentence, another issue we had with one-hot vectors is that they couldn't really understand similarity. So in that sentence, for example, where you have, I don't like mortals, but I like otters, implicitly in the semantic space, you would want mortals and otters to be quite close. But when you use to model those words as one-hot vectors, they are not similar at all. And so they are even orthogonal in that sense. And that's something that was a weakness of this previous approach. So here, I put an example of a pipeline from a blog by Sujit Pal, who is an amazing researcher. And that was done before the revolution of the transformers. And so he's explaining what's used to happen. So you had some text, then you had a tokenizer. Tokenizer effectively is just a way to split your sentence or split your document. Then you create a vocabulary like we have seen before with some one-hot vectors. And then you would vectorize each of those sentences with the one-hot vector method and your vocabulary. Again, you have no distributional semantics, so what that means really is that you had no full understanding of meaning of those words and similarity between concept, and that was a big weakness. In terms of self-supervised learning, what do we want to do? We want to be able to find representation for each word that makes sense in the semantic space. And once you have this, you can start understand language, and you can start being able to have, for example, a proximity between mortal and hotel that is greater than the proximity between mortal and model. So that's the type of understanding that the new approaches in terms of both deep learning and then later on transformers have brought to the field. And the objective, once you've created representation of those words that are more meaningful, the objective is then to use them to be able to do mathematics on them and draw conclusions. So that might be, for example, predicting the sentiment of a particular sentence. That might be extracting some subject of some sentences. You have countless applications of NLP that you could use if you had better representation of those words. Okay, language models. Language model is effectively a way for us to use sentences or text that is not annotated in order to create better representation of those words. So if you remember what we've seen at the beginning, we had two words that were very close that share nothing, and two words that were quite different that seems to be similar. When you're going to run language model, what you will do is that you will inject some text that is not annotated, a large amount of text, and at each step the model will try to predict what is the next word or what is the next token. I will use word and token interchangeably today, even though that's a little bit more complicated, but at each step, the model is going to try to predict what is the next word that will appear. And if the model can predict correctly what is the next word that will appear, we will conclude that it has some understanding both of the meaning but also of language in general. And so when you have really great language models, what you notice is, for example, that they don't do much grammatical errors, because part of the process of learning what it is to predict the next word will also teach them a certain level of knowledge in grammar and so on. And so here I just put the equation, but that's really not important. What you're trying to predict with that model is either the full joint probability of a sequence of words, or you're trying to predict what will be the next word, considering the fact that you've seen the 5 previous words. And what is interesting is that you're using language models every day. You have them in your cell phones every day when you have I don't know how they call this, but the completion of your text. You have them in Google. When you search in Google, you will see a number of propositions that appears that you haven't typed. Most of them will be coming from language model. More or less advanced, obviously, but from language model. Okay, and all of this idea of trying to find representation that are meaningful is really coming from computational linguistics and from the expertise of people who have been studying language for a long time. At the beginning of the revolution in deep learning, there was still some, how can I say that? Aggressivity on both sides, saying, okay, you will never be able to understand language, or yes, what you're doing is just statistics. It's not actually understanding of language, but we have to face the fact that those models have improved so much that a large part of this field has now moved to deep learning. Okay, and what you see there are two results of the creation of representation for those words. I mentioned before, we are trying to create vectors that make sense. And what you can see there is that those words are not synonyms. They are in the same space. so you could call this a semantic space. So they refer to objects that live in the same space. And even looking at them like this, you can have an idea of the fact that they are not complete opposite, that some understanding was pulled from the language model and put into the creation of those vectors. Any questions at this point? Nope? Yeah.
What does each number in each row represent?
Okay, so those numbers as such, as they don't really mean anything. It's more the fact that they end up in a particular space, in this case in 7 dimension, where other words of similar meaning will also belong. So they are more meaningful in terms of how different they are from, let's say, their synonym or their hypernym than meaningful as the numbers themselves. So basically you have numbers between -1 and +1, and all of this is normalized, but similar words end up having similar value for their vectors. Yeah.
How analogous is this to word embedding? I'm guessing you're probably going to...
Yeah, those are exactly word embeddings.
Okay.
So you could create word embeddings from different techniques, really.
Yes.
But yes, the result are word embeddings. Yeah.
When you create the semantic spaces,
Yeah.
if you train based on, let's say, like blog on Reddit, it's going to be very different when you train based on legal documents and something like that. Is there some kind of like meta understanding of what's going to happen?
Yeah, so I will come back to this, but some of those word vectors were created on gigantic amount of data. And so back then, in 2014, there was a Google corpus that had been created by Google, and based on that Google corpus that had 300 billion words in it, they had created the word vectors that were called Glove back then. There were Glove, there were Word2Vec, there were several versions of them. But if you want to have word vectors that are really specialized for your topic, you can fine-tune those word vectors on a specific vocabulary or a specific data set.
If a word has got more than one meaning, then presumably you're given a different set of values.
Yes.
For the same word.
Yes, we'll talk about that later, but that was precisely one of the advances of transformers compared to the previous version that were static word vectors. So that's partly the difference. Yeah.
How do you account for like different spelling? Like let's say in American English spelling, like for the same word, do you use the same vector?
Yeah. So
Armor or something like that?
So it depends on the particular technique.
Yeah.
But what will happen is that if those words, again, if you see that sentence here, you shall know a word by the company it keeps. What will tend to happen is when people make mistake, let's say they write mortal with two L's, they will still use it in the same context as mortal with one. So even though those words are different, they will end up in the same semantic space. And so they will have similar vectors. Okay, maybe we'll come back to questions after, later. Okay, so Word2Vec, someone mentioned Word2Vec. That was the model, well, the second model that really had a big impact on the computational linguistic field. What it was trying to do really is try to predict what is a word based on its context, and that's what we've just described. What really shocked me back then when that paper was published was the fact that you could start doing actual mathematics on it. And so when you see the equation further down, when you were using the vector for the word king, you remove the word man and you add the word woman, the resulting vector was very close from the vector of queen, which makes sense from the semantic space to the mathematical space. And to be honest, the first time I've heard this, I didn't believe it, and I went and tried, and indeed, it was relatively close. And the better your word vector are, the more you will be able to make conclusions like this. And we have an expert here of knowledge graph. Maybe he can talk about this later on during the panel. But that's definitely a way to try to make conclusions based on text. Okay, so the next few years, 2013 to 2016, were marked really by a almost standard NLP setup. People were looking for better word vectors. That means larger amount of text that is better, of a better quality. Because the first version of word vectors, for example, were using things like common crawl, but that version of common crawl wasn't really cleaned. And so you had things like HTML tag and things like that. So people tried to create better word vectors. With those better word vectors, they tried to create larger language model and better language model with different version. Here you have RNN, LSTM, GRUs, and sec-to-sec. All of those are basically type of models that you can use for your language models. And then with those better word vectors, better language models, they could do better prediction. So that's when things like sentiment analysis start converging toward really better results, but also named entity recognition. That was a big issue and big field of research. All of this started getting better and better around 2016. And so here you see the issue with the previous generation of model, RNN, which are recurrent neural network, and sec-to-sec, which are models. I won't get into the details of this, but this is a sequence-to-sequence model. What that means is that you would give it a sentence. Let's say for machine translation, you would give a sec-to-sec model a sentence in French. Then with those vector representations that we had here, we would create a vector, and you would feed that vector to a second neural network, and that second neural network would try using this vector to translate it, for example, into English. And that's what they were called sec-to-sec. It's a sequence-to-sequence, because you would feed a sequence to it, and you would expect a sequence at the other side. And so the problem with this is that in order to create those models, so what you see there on this page is a sentence where we are trying to predict the next word here. So we already have the student open there, and we don't know if it's which word it is, but it will put probability on different words. And so the problem with those sec-to-sec models in particular was that it was trying to capture all the information from the sentence from the beginning to that point into a lower dimension and just one vector. And that was one problem of traditional model before. They only had access to the last vector, meaning the vector here in H4 was the only vector you actually had access to try to predict the next word. And so what transformers, attention and transformers have tried to do is to give the model a better routing of information so that it can pick the information from whatever word that they need to be able to make the next prediction. And so here you see a visualization of attention that was created initially for machine translation. That was where the big problem of condensing a sequence of information into just one vector, that where that problem was the most important to solve. And so what you see those links between the word we are looking at now, which is it, and it's making the link, and it's weighting the importance of all the words compared to the word we are looking at now. And so the word that will be more important for that it will have a higher importance. That's what attention is about. Yes?
Why did you pick layer 5 in particular? Or what would change if we were doing layer 1 or 6?
So that's almost a philosophical question. So in traditional transformers, well, let's say Bert-like transformers. So Bert is one of the most famous transformer model. People say that the layer just previous to the last layer is the best to encode the representation, because when you have a transformer model, generally at the last layer, it's trying to predict exactly what you want. And so you want a representation of that word or of that sequence that is at a higher level of abstraction so that it can be used in many different contexts. So for example, in that case, you could consider that that was a network with 6 layers. We pick the layer just before the last one to have a better representation. Okay, so this was the paper that really changed everything in the NLP space. That was, it's called Attention is All You Need. It's an end-to-end model. What's interesting is that this model was published in 2017. Then, based on this model, many different models were published by different labs. So that one originally came from Google, but then you've probably heard about GPT and GPT-2 and GPT-3. What is interesting is that GPT-3 is basically just half of this model, is the right-hand side of that model. And Bert, which was the other very popular model, is the left-hand side. So this is, again, a model that, a type of models that are called encoder-decoder. So on one side, it's learning the representation. On the next side, it's trying to predict something. And so this model that was the original one is actually very close from one of the most advanced models even now, which is called T5, that you may have heard about. And one thing that I found personally interesting is that though there are always, let's say, lab debates or preferred affiliation, what you will see with T5, which is a Google model, is that it's also now included into some models that are coming out of NVIDIA or out of Facebook, which is relatively rare and for me gives some information about whether that model is actually useful or not. Yes?
Are all translation challenges the same, or are there particular challenges translating from one language to another?
So that's an interesting question, because one thing that Google in particular has been working on is the fact that you could create multi-language models, because in the end you have word vectors. So they are not French or English. If you can find a multi-language word vector for a concept, then you could do translation that they called zero-shot translation, meaning you could translate, let's say, French to Irish, even though you had no training data to train that model, because you would go through directly through the word vectors. Okay, and so this is the math that is happening behind. So this is referred most of the time as self-attention. Why this is self-attention is because you start with a vector, so an input to your model. In that case, the input is X here. And you make a projection of that input with 3 different matrices. So WQ, WK, and WV. And then you calculate the dot product between Q and K. And that's what we call Q the query and K the key. And the idea is that when you multiply 2 different representations of the same sentence, say, what you will learn are those matrices, those W matrices, and you will learn to route information from one word to the word that is the most relevant to it. So I know that might seem a little bit abstract. You're not alone in that thinking, but think about it as a database. You have a queue, you have a query, so you make a query, Then that query effectively tries different keys and finds the keys that correspond to that query. And it's only if the keys correspond that the value is released. That's effectively what's happening. The dot product is just a similarity measure, and then the softmax will create a weighted value of all the words that you have in order to create a better representation of each word at each step. Okay, from there, so that was the transformers. I'm not diving into T5 or GPT-3. Like I mentioned, GPT-3 is the right-hand side of the original model of T5. Bert is the left-hand side. Then you have dozens of refinement, but at a higher level, they all use dot product scaled attention. What is more surprising, though, is that this architecture that was created specifically for natural language processing also turned out to be working really well in computer vision. And so what you see there is the paper that really opened up the space for the use of transformers into computer vision. So that paper is generally used to show how you can get from an image to a transformer-based representation on which you can make conclusion, you can make segmentation, you can make prediction about what the image is, and so on. And what you see there is very simple. You take an image, you split it in 16, or you split it in a number of different patches. Then you do a projection with a random matrix at the beginning, but that matrix you will progressively learn it to learn that projection. And then you add something that was created by the previous transformers that I didn't talk about, which is the positional encoding. Because another problem of RNN, sec-to-sec, and those other models were that they didn't have a way to get accelerated, because you needed to have the output of the previous step to get to the next step. What many transformers have done is that they have used a system called masking, where you start from a sentence, you mask a few words or a few tokens from it, and then you try to predict everything in one go. And so, because you still need the information about which word happened before which other word, what they have done is they have added to the vectors a position vector. That means that the first word will be added a representation that means this is the first word of the sentence. Same thing for the 15th word. Then the model will have both the ability to predict in one go, but also the ability to look at which position the word was. And so they have done the same for vision, and it turned out to work great. Again, I'm not going to talk about leaderboard right now, but there might be some expert in the room. They can talk about it later if you want. But you can see on the other side that this was just using the left-hand side of the model, which is basically the transformer encoder. And there is a way to go even further to combine both type of representations. We have talked about creating representation for text with those models. We just talked about creating representation for images. Here you have a bimodality model that is co-learning both text representation and image representation. And so what you have there is that on the top-hand side of the model, you feed a description of an image, and then you also feed the image itself. And both the transformer model, the text transformer model, and the image transformer model will be learned together, because the image should give a very high score to its own description in the vector space. Does that make sense? Yeah. Okay, and so they can use supervised learning or semi-supervised learning to basically create better and better representation, both of the text side and of the image side, and create better and better vectors. And that was also quite revolutionary. Okay, so now we are talking about creating representation for text. Now we are going to talk about creating representation for graphs and node inside graph. So I'll go fast about the background. I don't know if I need to dive too deep into this, but graph theory is not from 2013. It started, hundreds of years ago. And the way it works generally is that you model graph as a set of vertices. So a vertex is a node and edges, and they create a structure. So that structure can be either observed, or you can decide what type of structure you want to give to your data and project your own vision of the structure on it. But what is interesting is that all those companies that you see here have basically been created between 2000 and 2015, and they were all at their core companies that were built on the previous generation of graph analytics. So Google was built on top of PageRank initially, which is a graph algorithm. LinkedIn and Facebook were basically based on the principle of homophily, which is coming from social network analytics. Pinterest is also, like TikTok, has become now a network of interest. And then Darktrace is basically a company in the anti-fraud space that is, among other tools, using graph analytics to detect intruders. So it's a huge market, huge companies, and they are quite active. Okay, so what type of problem can you deal with when you're using graph? Traditionally, you have the following. You have node classification. So if I have a social network, can I see, for example, who is, let's say, a barber, or who is a buyer for a particular product? You have node clustering. So can I identify a community from a network of people or a network of product? You have influence maximization. So this is at the core what PageRank was linked to. So can I understand who is the most influential node in a network of people or even a network of information? And then you have link prediction. And that one, for example, is pretty much from what I've heard is used at eBay in order to understand which product should someone be recommended to buy. And again, we are going to go from those traditional approach to a more representation-based approach, and that's really part of the progress in the last 5 years. So we'll look for representation that encodes the fact that nodes in a graph that are similar should have similar vector representations. And so that's what you see there. On the left, you have the graph where U and V are directly connected, so they are closed in the graph space. And on the right, you have the d-dimensional embedding space, and you want them to be closed as well. The problem with graph is you have no canonical ordering of the nodes. So you don't know, when you're creating a graph, generally you have to create a matrix, and with that matrix you will give order or a name to each node. But the structure itself doesn't change if you change the order of those nodes. But obviously the matrix is changing. And so when you're dealing with graph, you want to apply transformation, mathematical transformation, that wouldn't change the output of your program if you were just to change the order of the node. Does that make sense? And so that's where the concept, or almost the discipline of geometric deep learning is arising from, is the fact that you have some transformation of the data of your problem that are invariant or equivariant, meaning that you could change order of the set of elements you're dealing with without changing the outcome. And if you think about it, for example, if you have a network of customers and each customer has a customer ID, and you can see all their buyings for the last year, if tomorrow you just change their customer ID, you don't expect their behavior to change. So the ordering is completely arbitrary. And so you need transformation that are taking into account the specific aspect of graph that ordering shouldn't impact some of the outcome.
Sorry.
Yeah.
Just on that last point. Sorry. When you encode the graph from the spatial domain into this n-dimensional matrix,
Yeah.
and let's say you do move the node around in space, would that change the encoding?
No, it shouldn't. That's precisely the objective. It shouldn't.
But the node, it doesn't live in any space. It's just visual representation we have here.
Yeah, but
There's no distance between nodes, or there's no, like one is above the other. Or anything.
so the distance, if you change the distance, you might have a different result. But if you change the labeling, you shouldn't have any difference. And so a graph, basically, at a mathematical level, is effectively a matrix. You can take it as an adjacency matrix, where you have one node, and either that node is connected to others or it's not connected to others.
Exactly.
And so the ordering in that matrix, at which row you put which node, shouldn't have any impact.
Yeah. Okay.
So where's the information on the distance between 2 points? Is it within
So,
the matrix itself, the numbers in the matrix?
so that depends on your problem. Yes, sometimes you can do that. Because you can have a distance in the real world that you want to embed into that graph. And in that case, for example, the edges between those two nodes will have a particular length. Mm-hmm. Otherwise, if you don't encode distance as a primary object into your graph, everything will be basically equidistant to start with in terms of their neighbors, not in terms of other nodes inside the graph. Okay, so what the graph neural network are doing is effectively reuse the structure of the graph in order to compute features for each of the nodes. So they start with features that you know, and then you have neural networks, multi-layers neural networks that will aggregate the information for each node in order to deduce a good feature representation for that particular node. So for example, if you look on the left-hand side, you have the original graph, right? And so you have the target node that we are going to do something about, or maybe do a prediction or classify it. That node is node A. So we look at which node is node A connected to. And in that case, we are looking at nodes first that are connected by just one hop. So basically a distance of 1. And in that case, you have node B, C, and D. And so on the graph neural network you're creating, you see at the first level you have B, C, and D. But B is also connected to A and C. And so what the model will do is for each of those nodes, it will find a method of aggregation of the information coming from their neighbors, and then propagate that information until the information reach A. And the neural network itself will have some projections that you will learn, but those projections or those weights inside the neural network will be shared by all the nodes. And that's one way you can deal with the explosion of computation you would have if you had a separate neural network for each one of them. That's actually an issue also with traditional transformers, but maybe we'll talk about this later. Okay, and so that was a very, well, I shouldn't say the very first because you never know. I don't think Schmid-Huber is here, but you never know. Semi-supervised classification with graph convolutional network by Kipf and Welling was a paper that made a big impact in the community. It was effectively, there is a lot of math that I won't explain right now. But what was happening at a lower level is that they found a way to do operation on the node that are similar to convolution type of operations, and that preserve this equivariant and invariant condition that we talked about before. And so what's happening there is actually very simple. You see the H value here. HV, for example, is a representation, so a vector for the node V that we are trying to deduce. And so inside this neural network that we show, you had several layers. And so what you do is that you take the previous representation at the previous layer. So here we are looking at layer K. So we take the representation that was found at layer K-1. We'll multiply it by a matrix that staying the same for every node. And then we add this to basically a weighted value of the representation of all the nodes that this particular node was connected to. So that means if we look at node C on the right, we'll add the value of A at the previous iteration, and we'll add this to a weighted value of all the other nodes that were connected to that node. And then we pass this through another transformation, and F, W, and B there, which are transformations, all those transformations are the same for every node in the network, which allow you to share some weights and eliminate some computation. So that was the GCN vector. The second one was by Leskovec, which is one of the experts that has been very vocal about graph even before GNN, and that is a head scientist at Pinterest, I think. And in that case, what we are doing is first we do some sampling. It was particularly focused on very large graphs where you may have some issues in terms of number of computations. And so you do some sampling, and instead of adding the value of instead of really adding the value of the node at the previous iteration and an average of the other nodes, here it's basically concatenating the value at the previous iteration with an aggregate value. And that aggregate value can change. The model will stay the same whether you use, for example, a max value. It's still the same type of model. What is interesting though is that if you just take the mean as the aggregation function, then you go back to a model that is very close from the GCN models that we've seen before. And then again, you multiply this by another transformation that is shared across nodes. The last one is graph attention networks, and this one is the first one that really is trying to combine the graph approach and the attention approach. And here you see an image of how this attention is being incorporated. So to conclude, really for me, the most impactful thing that came out of this line of research, both on attention and graph, is what has been done by DeepMind since 2021 with Alphafold 2. I don't know if you've heard about it, but effectively Alphafold 2 has a model that from the paper that they publish in Nature. They have a module inside their protein prediction model that is called EvoFormer, that is effectively in practice using both self-attention and also graph predictions. So that was it. If you have any question, you can shoot.